Landscape trees may develop defects in their branch and crown architecture due to poor growing conditions, to storm damage, or to lack of structural pruning. Some species are more prone to developing structural defects that could result in branch failures or whole tree failures that could potentially harm people, damage property, or destroy the tree as a landscape asset. Although we would prefer to use preventive structural pruning of trees to prevent the development of defects, sometimes we have to install support systems in order to lower the risk of branch or crown failures in order to protect assets, people, and property. Supplemental support systems are devices placed in trees to reduce the risk of branch, leader, or whole tree failure. The types of supplemental support systems include cabling, bracing, and guying. We will look at some examples of supplemental support systems that have been installed in trees here on campus. This mature green ash did not receive periodic structural pruning when it was young. As a result, it has developed multiple codominant leaders and long overextended branches that place a lot of weight in the perimeter of the crown and therefore place a lot of stress on the attachments of those leaders and branches low on the trunk. Green ash is very susceptible to developing included bark, which is a branch attachment deformity that weakens the attachment of the branch. In the case of this specimen, this tree is located in a wide open area where it gets a lot of wind. This would increase the risk of a branch failure that could possibly damage the tree or cause harm to nearby structures or people. In this case, the risk was not able to be mitigated by pruning alone, and the decision was made to place a support cable in the tree. In this case, the type of support cable that was installed is known as a non-invasive dynamic cable, sold under the trade name of the Cobra system. This particular type of support cable spans between two of the primary codominant leaders in the tree and helps to limit movement of the two major codominant leaders and possibly reduce the risk of a stem failure. If you look closely over my shoulder, you can see the dynamic support cable extending horizontally between two major leaders in the tree. The purpose of the support cable is to limit the movement of the two primary leaders relative to one another, and thereby minimizing the stress that's experienced from movement on the attachment of the codominant leaders with one another. The flexibility in the dynamic cable allows limited movement of the two leaders. This is thought to be of advantage to the tree in the development of reaction wood and response growth that will strengthen the leaders, but yet not compromise the attachment between the two. Dynamic support cables are suitable for large leaders that need some supplemental support, but yet do not have compounding defects of included bark or cracking in the union. The dynamic support cable is fabricated from interwoven polyester fibers. This gives the cable its stretch and its dynamic properties. This particular model of dynamic support cable is also considered non-invasive for the means in which it attaches to the tree. Rather than securing the cable to the supported stems using lag hooks or eye bolts, the support cable is wrapped around each stem that is being supported by the cable. The wraparound design of this support cable could still potentially cause damage to the stems that it's supporting from either girdling or chafing of the cable wrapping around the perimeter of the stem. To help minimize that type of injury, the wraparound system typically has a widening band that helps to dissipate that load, and then has a self-adjusting feature that allows the size of the loop to increase as the stem grows larger in size. Even with these features, it's important to periodically inspect these types of systems to ensure that they're not damaging the stems. Once installed, the support cable will limit the movement of the two stems relative to one another and reduce the loading and strain that is experienced by the compromised union below the fork. Support cables are not limited to use on large maturing overstory trees. They can also be an important preservation strategy for smaller ornamentals that have developed defects. In this case, we have a mature Japanese maple that developed early on in its life codominant leaders with a significant bark inclusion. On this particular specimen, the choice was made to install a static steel support cable. This is different than the dynamic cable in that it does not have much flexibility and therefore holds the two stems more rigidly. Static support cables would be the preferred solution when you have a tree that has developed significant bark inclusion or cracks in the union that you seek to support. However, understand that these static rigid systems do limit movement of the stems and therefore may deter development of reaction wood and response growth. Here you can see the static support cable spanning between 2 leaders in the Japanese maple. Notice that the support cable is not oriented horizontally to the ground, but rather is oriented in a way such that it is perpendicular to the angle of attachment between the 2 stems being supported. In this case, an invasive anchor is being used that comprises an eye bolt that is secured through the stem with a nut and a washer. This is a more sturdy and stable anchor means for a cable, but because it is invasive, it could potentially induce decay in the wood that is injured when drilling the porthole. For that reason, invasive anchors should be limited to stems that do not currently have decay or only be used in species that are highly resistant to wood decay after injury. Here we have all the primary components of a static support cable that is fabricated from steel hardware. We have the 7-strand, 1/4 inch diameter woven steel cable. We have the thimble that serves as the connecting vise between the cable and the eye in the bolt. The eye bolt, the washer, and the nut. The way that the cable is installed is that an appropriate length of cable is cut to span the distance between the 2 stems being supported, and then a pilot hole is drilled through each of the stems at the point where the eye bolts will be attached to the cable. So the pilot hole is drilled through the stem. The eye bolt is then inserted into the stem. It is then secured in place with a nut and washer. That is then secured snugly against the tree, not having any excess space between the eye and the eye bolt, and then cutting off any excess amount of the eye bolt on the other side of the stem with a hacksaw. With this particular design here, this is a hand splice, and so the 7 strands of the cable are unwoven, passed through the thimble and the eye, and then spliced back on itself. But more recently, there have been the use of a dead end grip that is used to secure the cable to the eye bolt. Here's an example of a termination for a cable that's been fabricated with a dead end quick grip or quick wrap. This is what it looks like when it has been spliced. This is what the dead end grip looks like before being spliced. The way that this works is that it is inserted through the eye bolt. It is placed within the cradle of a thimble, and then each leg of the grip is wrapped spirally around the cable and eventually forming a very tight grip around the cable. If you look closely, you can see the legs of the quick wrap spiraling around the section of the cable, securing it in place. A specific type of cable has to be used if it is a hand splice or if it is a dead end grips type. With the dead end grip type, you must use what is known as an EHS extra high strength cable. In contrast, when doing a hand splice, you must use a soft steel cable. The reason it's called soft cable is that each strand in the cable is relatively flexible, and that makes it easy to bend by hand to complete the hand splice. The extra high strength cable has a much higher tensile strength than the soft lay cable, but you cannot intermix hand splicing or quick wraps between the 2 types of cable materials. The quick wrap is only intended for the EHS, and the hand splice is only intended for the soft lay cable. Regardless of hardware type, all support cables require periodic inspection to make sure that the hardware is properly installed and intact. Regardless of materials, all supplemental support cables must be periodically inspected. At that time, it is important to inspect the integrity of the materials, all of the hardware that's involved, the cable and the anchor points, as well as to inspect the height of the cable in the tree. Because trees grow taller over time, it may be necessary to adjust the positioning of the support cable. In most cases, that would entail installing an additional support cable higher in the crown of the tree and leaving the initial cable installed below where it was originally installed. With static invasive support cables, that typically means installing a new cable higher in the crown at the appropriate height above the stem union. However, with non-invasive dynamic cables, it may be permissible to remove the cable and move it up into the crown to a new position that's appropriate to provide supplemental support. Sometimes the size of the tree or the severity of the defect in it necessitates multiple support cables. In this case, we have a mature hackberry that has a very large scaffold branch that has developed a bark inclusion and crack. The decision was made to install a system of support cables to not only support the weight of the branch, but also to manage the torsional strain from the branch moving in horizontal planes as well as vertical planes. Closer examination of the tree shows the severity of the bark inclusion and the cracking associated with the weak union of the scaffold branch. The bark inclusion emanates all the way from the base of the branch, passing down almost along the entire length of the trunk and ending within a couple of feet of ground level. This would be a branch attachment that's very weak and would be very prone to failure, either under the branch's own weight or in inclement weather. So not only do you have the vertical stress of the weight of the branch, but when the branch is being moved side to side in high winds, that is also going to be putting horizontal or torsional stress on the branch attachment. The support cables are difficult to see in this tree because it's a large tree and therefore they're situated high above the ground, but these are also static, small diameter steel support cables, and so that makes them more difficult to see as well. But there are two separate support cables in this tree. They are both attached to the scaffold branch, and then they are connected to two other leaders in the primary portion of the tree. So in this way, they're not only providing some vertical support for the weight of the branch, but they're also providing some support to the horizontal torsional stress from the scaffold branch moving side to side in the wind. The anchor terminus of one of the support cables can be seen about 2/3 of the distance out onto the support cable, and then it passes upward through the crown and it eventually is anchored and terminated back on one of the primary upright leaders about 2/3 of the distance above the point where the scaffold branch diverges from the main trunk. From this angle, you may be able to see the point where the cables cross one another. They're not in contact with one another. They're separated by several feet of vertical space, but this crisscrossing pattern, what that helps to do is to provide additional horizontal stability to the branch. In this way, you're triangulating the support and limiting the horizontal movement of that scaffold branch by having it tied into two separate points in the tree. The second main type of supplemental support system for trees is bracing or brace rods. In contrast to cables, which support weak or defective unions above the point of attachment, brace rods provide supplemental support at or just below the defective union. This Japanese maple developed very serious codominant leaders early on in its life. Eventually, bark inclusion occurred here, and there has been some cracking since then. As a result, one or both stems may be at risk of failure. To reduce the risk of this failure, brace rods were installed in the weak union to provide supplemental support along with the cable above. Supplemental cables are generally regarded as providing the best level of supplemental support for weak unions. However, it may be impossible to properly install a cable between two stems that are narrowly attached and do not have space for a span of cable between them. In those cases, brace rods may be the only option to provide supplemental support. Brace rods can be fabricated using two different types of materials. One is called a through brace because the brace passes completely through both stems and is secured on either end with a nut and washer. The other is called a dead end brace. The dead end brace would be similar to a lag decking screw in which the threads of the lag are embedding in the fibers and holding them in place relative to one another, limiting the movement of the stem. In contrast with the through brace, the pilot hole is drilled into the two stems, the brace rod passes completely through, and the support is provided by the pressure against the washer and the nut on each side of the stem. On this Japanese maple, a through brace was installed about 15 years ago. It is now getting to a size where additional brace rods may be necessary to meet the ANSI A300 specification for this size stems. Closer inspection of the brace rod shows how the tree has responded to the installation with callus and woundwood formation. Here we can see where the brace rod spans between the two stems in the area above the bark inclusion. On the right, you can see a very prominent ridge of woundwood that has developed around the brace rod where it enters into the stem. If we walk around and we look at where the terminus of the brace rod was on each outsides of the stems, you can see that it's just barely visible inside the end of the brace rod and then the washer. And so callus and woundwood has formed around the nut and the washer in the years since installation, almost entirely closing over the end of the brace rod. You can see the middle portion of the brace rod in a little closer detail, and you can see the woundwood that has developed on both stems. And then looking at the terminus of the brace rod on the outside of the other stem, you can see that it has almost entirely sealed over. There's just a little bit of the end of the brace rod that's still visible poking out of the woundwood. So I don't know what the condition of the wood would be inside these stems, but I would speculate that there's been very limited discoloration and decay of the wood because this is a high vitality specimen and Japanese maple is relatively intolerant to decay. This mature Japanese Zelkova has a very significant bark inclusion as a result of its codominant growth habit. As you can see from the growth form, there are numerous codominant leaders in the tree that is typical for the species and are likely to develop when the tree is not on a structural pruning regime when it's young. Because this tree is open grown, it has also developed a very broad and expansive crown that has placed additional weight strain upon the union of the codominant leaders. As a result, the stem developed a crack along with the included bark. 2 brace rods have been installed in this tree in an effort to reduce the risk of the failure of the 2 primary stems associated with the bark inclusion. We'll take a closer look at this brace rod installation. This tree is a work in progress. It is not completely up to ANSI A300 standards for brace rod installation, and more brace rods will be installed in the future to meet that requirement. Here you can see the positioning of the 2 through braces that were installed in this tree about 1 year ago. At this point, 2 brace rods have been installed below the union in the area of the bark inclusion and cracking that you can see on the stem. The top brace is here, the bottom brace is here. Eventually a 3rd brace will be installed up above the divergence of the 2 stems to meet ANSI A300 standards. Here you can see the significance of the bark inclusion between the two primary codominant leaders. This bark inclusion has developed cracking in it, and this is a seam that the tree has not been able to seal over and to form a fused layer of wood around. This type of bark inclusion tends to result in a persistent seam, and oftentimes associated with that seam is discoloration and decay of the wood. You can see here how the tree has put on some additional callus and wound wood development over the last year around the perimeter of the washer and the nut. In this particular case, we did not countersink the washers against the sapwood by removing bark. Everything that you're seeing here is the natural development of the callus and wound wood. And so what we'll anticipate as time goes on in additional annual growth increments, we will see additional callus and wound wood development around the washer, and eventually we'll see closure of the wound wood around the nut and washer, and eventually there will be completely sealed into the sapwood of the trunk of the tree. There does appear to be a bit of bacterial slime fluxing that was associated with this lower brace rod installation. It does not look to be an active bacterial slime flux. I can see the discoloration from last growing season, but it seems that that fluxing has dried up now, and it doesn't look like it's going to persist. Crown and branch failures due to structural defects or inclement weather are a major threat to mature trees. Associated with inclement weather is another type of threat to mature trees, and that is the risk of lightning strike. Because mature trees grow to very tall heights, they are very commonly attractive to lightning strikes. This problem is especially compounded when you have open-grown trees that are not surrounded by buildings or other vegetation, and they're isolated out and are more likely to draw lightning strikes. The frequency of lightning strikes varies with different parts of the country. Some parts of the country have very frequent thunderstorms, and as a result, lightning strikes of trees are more common. It's also believed that some species are more likely to be struck by lightning, such as tulip poplar, white oak, white pine, loblolly pine, and other large maturing trees. However, this may be just a function of their abundance in the landscape and may not necessarily be associated to their species being particularly attractive to lightning strikes. Lightning strikes may cause fire and physical destruction of trees in a very intense lightning strike, but more commonly what happens is that the lightning strike causes chronic stress for the tree that puts it into a state of decline due to disruption of the vascular system and the attraction of the lightning strike wound to pathogens and wood-boring pests. For high-value specimen trees, a lightning protection system might be a good investment to reduce the risk of lightning injury and damage to the tree. We will look at a lightning protection system on a highly valued tree on the campus of Virginia Tech. This is a tree known as the allwood oak. It is a bur oak, Quercus macrocarpa, who was named for the horticulture professor who planted the tree in 1895. This tree resides on the drill field in front of Burris Hall and is one of the most widely recognized trees on campus. A lightning protection system does not prevent a lightning strike, but rather facilitates a path to ground for the lightning strike. The lightning protection system is fabricated from copper-clad metals that comprise an air terminal, a conductor, a ground terminal, and a ground rod. In a lightning strike event, a charge forms in the clouds above the tree and separates positive and negative charges. A stepped leader moves out of the cloud down towards the tree, seeking a path to ground. A streamer of opposite charge moves up out of the crown of the tree and makes connection with the charge coming down out of the cloud, completing the circuit and allowing a path to ground for the discharge of the lightning strike. That lightning strike usually passes through the sapwood of the upper terminal portions of the branches or the leader passes down through the branches, down through the trunk, and then out into the root system and eventually into the ground. Along this path from the peak of the tree to the base of the root system, there's often significant sapwood injury and bark damage. As a result, the vascular system of the tree is compromised and wounds are created that are open for pests and pathogens. Here I have some of the primary hardware components of a lightning protection system. At the peak of the crown of the tree will be positioned the air terminal, which is a rigid copper-clad metal device that is the initial contact point for the lightning discharge. Attached to it is a copper-clad woven wire cable that stretches down along the leader and then to the trunk, and eventually into a trench that's dug in the soil to extend the conductor out into the soil to attach to the ground rod. The ground rod is a copper-clad steel rod that is driven 8 to 10 feet into the ground at a minimum distance away from the tree to ensure that the lightning discharge will not damage large buttress roots. Holding the copper conductor in place as it passes from the peak of the tree at the air terminal down to the ground rod in the soil are standoffs or drive fasteners. These are copper-clad nails that have a fixture that clasps onto and supports the cable and then is tacked into the tree, holding the cable off of the bark by about 2 to 3 inches. This helps to ensure that the lightning strike, as it is moving from the air terminal down the cable, will not easily move into the bark. Sometimes there are slight discharges into these drive fasteners during a lightning strike, but typically the damage will be much less severe than it would be if it was an unabated lightning strike. A lightning protection system does not prevent a tree from being struck by lightning. In fact, it actually encourages a lightning strike because of the high conductivity of the copper-clad hardware that makes up the system. For this reason, it is very important that the lightning protection system be properly installed according to ANSI A300 standards and that it be periodically inspected to ensure that it's properly bonded and grounded. In the case that the system is broken or not properly bonded or grounded, there's actually the chance that you could increase the risk of the tree being struck and damaged by a lightning strike. As we take a look at the lightning protection system that is in the all-wood oak, it comprises 2 conductors that diverge from the ground conductor just a couple feet above ground. One of the conductors passes around the left side of the trunk and the other fork passes around the right side. The reason for having 2 conductors on the tree is because of the size and the spread of the crown. There is a limited area around each conductor that will attract a lightning strike, and if the conductor and the air terminals are too far apart, then the tree will not be provided sufficient protection. In addition to the 2 primary conductors in the tree, these subsequently fork out into some secondary conductors. And you can see here that one of these secondary conductors runs out the left side of one of the upright leaders, and another one goes out the right side. Each of these will have an air terminal that it's associated with. And here you can see the other primary conductor. There has been some vandalism on this system. You can see where some of the drive fastener standoffs have been pulled out of the trunk of the tree because of people handling the conductor. In an effort to try to deter that, we have placed some sticky grease material on the cable to make it unpleasant to touch the conductor. And that might be a practice that's necessary in high use areas like a college campus. So here is the other primary conductor, and it is passing up along one of the high-reaching and far-spreading scaffold limbs on the tree. Not visible in this tree because of the height above ground is a series of support cables. Support cables that are fabricated from steel are very conductive of lightning strikes, and as a result, anytime that you have a tree with a lightning protection system installed in it that also has support cables, those support cables must also be bonded into the lightning protection system. What that means is the attachment of a fixture that makes electrical connection between the support cable and one of the conductors of the lightning protection system. So each one of the 3 support cables that are in this tree has been bonded into either one of the primary or secondary conductors. Here you can see where the 2 primary conductors are spliced together, resulting in a single ground conductor. And you can see where the ground conductor passes into the soil. During the installation, a very narrow trench was carefully excavated radially out from the base of the tree. In this particular case, the ANSI A300 standard dictated that the ground rod that terminates the ground conductor would be situated out about 22 feet from the base of the tree. And so in this area right here, a hole was dug to allow the driving of the ground rod and then the attachment with another piece of hardware of the ground conductor to the ground rod, and then passing back towards the trunk of the tree, and then splicing back into the air conductors. Trees will outgrow lightning protection systems. Many mature trees have a low vitality and therefore are not growing at a very accelerated rate, but sometimes lightning protection systems are installed in relatively young, high vitality trees, and within a period of 5 to 10 years they can quite conceivably outgrow the protection cone provided by a lightning protection system. If that's the case, then upgrades need to be made to the lightning protection system to reposition air terminals higher in the crown of the tree, such that when that stepped leader of a lightning discharge comes in close proximity to the top of the crown of the tree, there will be the release of a streamer up from the air terminal that will be of sufficient length to reach the stepped leader and make contact with it above the crown, rather than allowing the stepped leader of the cloud discharge to first come in contact with a streamer that might be emanating from a branch that reaches high above the air terminal. Lightning protection systems can be tested for their conductivity by having a climber or someone in a bucket truck go up into the crown of the tree and attach one lead of a circuit to then attach to a piece of electrical cable that is positioned further down, and then an amp meter or a voltage meter can be attached to those 2 leads that are separated by the length of the air terminal, and then check the conductivity of the system. This will detect any breaks that might not be readily visible in the conductor up on the branches of the tree.